one more problem here. And we're going to say that we have 2,000, 250,000, 2,500,000, and 2.5 giga ohms. A lot of resistance. Very little current's going to flow through there, right? Okay. Can we figure out these big numbers? Let me put my glasses on because I'm going to be able to see all the zeros now. All right, so I'm going to turn it on. I'm going to hit clear twice. I put in 2,000 x minus 1 plus 250,000 x minus 1 plus 2,500,000 x minus 1 plus 2.5 giga is 2,500,000,000,000 x minus 1 is equal to 1,982.55 ohms. Lower than the smallest resistance, even though we think that 2 giga ohms would bring us up a lot higher than that. But remember, the lowest resistance is going to flow that much current, and each path provides lower and lower resistance to the total resistance. Okay. Now, let's do a problem where we're going to put our Ohm's law to work. Let's go back up here and let's put some different things in here. Let's say we're going to have, let's see here, let's put in 500. 750, 1,000, and 1,200 ohms. Everybody okay with that? Now let's add in, let's add in some other total. What's constant in parallel? Voltage. So if we had a voltage, let's say 500 volts. Then we would know two things in each branch, right? So 500 volts here, 500 volts here, 500 volts here, and 500 volts here. So now we know that we're going to go down, right? First of all, let's get our total resistance because that'll tell us our total current, right? Okay, so let's get our total resistance. So let's hit clear twice. We're going to put in 500 x minus 1 plus 750 x minus 1 plus 1,000. Wait a minute, I made a mistake. 750. 1,000. X minus 1 plus 1,200. X minus 1 is equal to, x minus 1 is equal to. What did you get? 3,450 is higher than 500 ohms. That's not possible. 193.5? I get 0.548, but that's a whole different thing. No big deal. So let's put in 193.548 ohms. So if we divide 500, now let me give you an example how this calculator works out so neat. Now I've got this resistance in here, but I want to divide by that, not use it first, right? So I'm going to put in 500 and ignore it. And I'm going to put in divide by, and now I'm going to put in second function, answer, enter, for equals. And I get 2.583333333333. So my current here is 2.58 500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-500-5 current. Now remember, the parallel circuits are current dividers. So when we get the current for each one of these branches, they should add up to 2.5833. Okay? So now let's go back and find our other currents. We can see the first one's going to be pretty easy. 500 divided by 500 is going to be 1 amp. Okay? 500 divided by 750 is going to be less than 1, right? 500 divided by 750 gives us a current flow of 0.6666. 0.66 continuously, right? Or 0.666667, somewhere way the hell out there. Now, you know what? I think I can figure this one out. 500 divided by 1,000. I'm not sure, but I'm pretty sure I can figure this one out. Yep, 0.5, 0.5 amps. On a quiz, would we answer 0.5 amps? No, we would never do that. We'd put it in proper engineering notation and say 500 milliamps, right? Same back here at 0.66, we would not put in 0.66 as an answer. We would put in 666.66 milliamps, right? 666.66 milliamps. We'd move the decimal place over 3 places to the right and go down 1 unit, which is milli. Okay, now, whoops. Okay, after yesterday, it's retraining me on what to do here. Okay, now, we've got 500 divided by 12. I can't do that one off the top of my head. 1,200 is equal to 0.41. And again, 66, or 2/3, is going to come into play. Now, I want to add all these currents up. So I'm going to add that plus 0.5 plus 0.6666666667 plus 1. And I'm going to add, I'm going to hit enter, and that's going to tell me the total, and it says, shocking, 2.583333333. Amazing, I tell you. Pure functional magic, I'm telling you. It comes out correct. Wow. While we're on this, could we get our powers? How would we get our powers? We just multiply I times E. That'll give us our power in each one of the branches. And on our power total, we can multiply our voltage times our current, get our total power. And power is always additive as long as we're talking about true power. Remember, true power and apparent power are not the same thing. Okay. We need to do one more, don't we? Let's do one more. Let me hit pause for a second. All right, we have an example from your workbook, and we have a total current of 4 amps, and we have total resistances. So this is no big deal. We can find our total resistance very quickly and easily. We're going to hit on, and we're going to hit clear twice just to make sure there's nothing in the memory. Then we're going to put in 50, x minus 1 plus 300, x minus 1 plus 100, x minus 1 plus 10, x minus 1 is equal to, x minus 1 is equal to, and we get a total of 7.5 ohms. Now, how does that help us? If we know that if we write PEIR next to every total, the totals, the resistor 1, resistor 2, resistor 3, for going up we multiply, right? So I got 7.5 in my calculator, I'm going to multiply times 4. And I get 30 volts. Voltage is? So we're going to plug in 30 volts everywhere. Now we have two totals in every branch, right? Exactly. So now we have 30, which is the hardest one? 30 divided by 50? We get 0.6 even. And then we're going to have 30 divided by 300. I think I can figure that one out. 0.1. What would we write? I started to write more stuff. What would I write if this were an answer on a quiz? 100 milliamps. Thank you. Very good. So 30 divided by 100. 0.3. It doesn't seem like that ought to come out to 0.3, does it? Okay, and then 30 divided by 10, I think we can figure that one out. What do you think? Just to make sure, 30 divided by 10. Yep, 3 whole. Now let's add these up. Do our cross check here. We have 3 plus 0.3 plus 0.1 plus 0.6 is equal to 4. Amazing, I tell you. Pure functional magic is still working. Okay, have we found out everything except the power? What amount of total power do we have? 120 watts. I almost hate writing watts. I teach AC, and it's like there's this rope attached to my arm that stops me when I want to write watts at the top. VAs, apparent power, whatever voltage and current are coming in, you multiply them together, you get VA. Volts times amps, you get VAs. And that's called apparent power, and that's what's coming into any circuit. What might be coming into the, now in the case of DC power and resistors only, true power and apparent power are the same number, theoretically. Okay? You'll never prove it to me, but that's okay. Okay. Now, let's stop so that you can see this again someday.